So Sirius, everyone knows Sirius. Years ago, a lot of people didn't know it, but it's actually become quite popular service. It's in many cars, as you are probably aware, and I see some are current subscribers. But a little background on the history of the company. In 1993, the FCC auctioned off 25 megahertz of bandwidth for a new concept. Basically, it was satellite radio to the car, which was never done before. And only two companies bid on bandwidth, and that was a company called CD Radio, which changed their names to Sirius, and then another company called XM Radio. And each company paid about $90 million, which was a bargain for 12.5 megahertz of bandwidth. People will pay upwards of $1 billion for that same amount of bandwidth. Years later, instead of fighting each other, they decided to merge, and that happened in 2008. And since then, we've been known as SiriusXM Radio. Sirius actually acquired XM. We became one company. Most people know it as transferring music to the car, but actually, as you just said, it supplies a lot of other data that a lot of people are not involved in. Movie times, map data, traffic information, navigation, map updates, all sorts of stuff that's in the background. Those are additional costs, but most people know it for the music content that is delivered to the cars. Okay. It was the first, and right now it's the only mobile satellite data service that is in existence. Nowadays, you do have a Starlink. That's really not intended to be a mobile service. That's more of a fixed orientation. So, and we've become quite successful. As I mentioned before, when I started with the company, we were 300 subscribers. We're at 35 million today. It's pretty much flattened out now. We've kind of saturated the market. We do gross about $9 billion in revenue, and we are a very profitable company. Slightly over $1 billion in profit every year. We're installed in about 85% of the cars. We don't want to be in 100% of the cars because there are certain cars that people buy that will never get them to become subscribers. Those are usually the very low end, cheaper cars where people just are on a budget and they can't afford to pay the monthly subscription fee. And what's this? Okay, so how do we do this? So Sirius uses satellites, and not only that, but we do have an IP streaming network. I'm not involved in that part of the company. And my talk is mostly going to be concentrated on the satellite side of SiriusXM, which for the most part is much more popular than our streaming services. I mean, everyone today, the streaming service, you get music, it's Spotify. It's not SiriusXM. So, and I don't know that area, so I'm going to just talk about the satellite side of it. So, the satellites. So there are these are geostationary satellites, and what that means is that if you look up in the sky and find a satellite, it's pretty much going to be there at the same exact spot the next day and the day prior, as opposed to a geosynchronous satellite, which would be there at a certain specific time, and then as time goes by, as it's moving around. These are they used to be geosynchronous, where they were in these polar orbits. Now we've moved to a geostationary. So that all it means is you got two satellites that provide our service, and they're up in the sky, and they stay within a box of around 10 kilometers on the side, and they do constant manipulation to try and make sure that they stay in this box. Every satellite has to do that. If you can't control your satellite, the FCC mandates that you have to deorbit your satellite. Okay, so that is a big part of Sirius, and that ultimately, believe it or not, dictates the life of the satellite. And I'll explain to you why. Where are they located? Well, at longitude, they're at 85 degrees and 115. What that means that there's, for each service, Sirius and the XM band, there is one satellite on the East Coast that provides signal coverage throughout the country. And there's another satellite on the West Coast that provides, again, throughout the country. And they basically overlap the entire United States. Okay, so I'll get to a picture on the next slide. What do these things look like? Well, they're about the size of a school bus. They weigh about 12,500 pounds. Half of that weight is fuel. And you might ask, well, what do you need fuel on a satellite? Well, I told you they had to stay in a box. So that fuel is constantly shooting these little exhaust nozzles in 3 dimensions to always maintain this location in the sky. And when you run out of fuel, you have to deorbit the satellite. So they have enough fuel on each of the satellites to last around 15 years or so. If it wasn't for that, they can pretty much stay in the sky indefinitely. But that is the life expectancy of a satellite, is around 15 years. What do they look like? Well, they're 27 feet tall. That's a small Victorian house. It's about that big. And this is basically right before it was loaded into a SpaceX rocket, which now basically has captured the entire satellite launch industry because they're dirt cheap compared to all other methods. Okay. When they are in orbit and they expand, their solar panels and their antennas, they are about the size of a small jumbo jet. They're 110 feet, 106 feet across with the solar panels, and a fairly large antenna that is sending information. There's a receive. This. I don't know if this is gonna. Okay, there's a receive antenna here, and this is a transmit antenna, and it sends down the signal down to the Earth. And this satellite is what's called a bent pipe design. All that means is that it takes the signal, does a simple translation in frequency, amplifies it, and sends it back down to Earth. Okay, it does no onboard processing. It's very simple. Okay, so obviously this is not to scale, but these satellites are sitting about 23,000 miles above the Earth, and they are pretty much stationary within that 10-kilometer on a side box. And here's the 85 and 105 longitude satellites. They are basically sitting around the equator with a focused beam of energy that covers primarily the United States, much of Canada, and much of Mexico.
How many satellites are there?
There's a total of 5 satellites. Okay, I think this is in this design here. I'll get to that in a second. There are 2 satellites per band. Okay. So we send up a signal to each of the satellites in 7 gigahertz and then translates it back down at 2.3 gigahertz. Okay. And those frequencies are convenient because the antennas become quite small. If you've ever seen a satellite antenna on your roof, they're about the size of a small hockey puck. Okay. And on the satellites are intentionally made to be very simple. They don't want any complexity because you can't fix them if they break. So they're intended to be very simple, and all they do is basically receive the signal and transmit in a different band. The satellites consist of what's called traveling wave tube amplifiers. These are very high power microwave amplifiers, and each one of them puts out 250 watts of power, and we have 32 of them. So if you do the math, it comes out to, I believe, 8,000 watts. Okay, so you have 8,000 watts of raw power, and then that goes into a fairly large antenna that has 33 dB of gain, which translates to 16 million watts. That's effective isotropic radiated power. So if you had an imaginary point source that can put out power, it's putting out 16 million watts. Now, the problem is it's at 23,000 miles, and because of path loss, this is basic physics, you receive on the ground 1 femtowatt. That's 1 to the e to the minus 15. So you started at 16 million and you got a very, very small. I think the energy of a fly flapping its wings is 1,000,000 times higher than that. Okay, so what does the power density look like? Well, from the satellite, they don't just blanketly, evenly spread out the power. They will concentrate the power based on these gradient lines on where the population is, and also limited to the physics of antenna design. But you'll see that most of the power is actually sent along the East Coast and the West Coast, because that's where there's a lot of population density. Okay, and each of the satellites does this. There's other factors involved in terms of what's called look angle. The best reception would be pretty much right at the center of the country rather than on an angle, because you're going to get less blockage from buildings and trees. Okay. So not only do we have 2 satellites that are used, but there's also a terrestrial network that's involved. So when you go into Manhattan, there's so many tall buildings, it's very difficult to get satellite reception. And the same thing happens with GPS, any kind of satellite reception. So, but yet, if you had Sirius service and you go into Manhattan or any big city, you don't notice the signal dropping out. That is because there is a third component that is used to basically fill these areas where it's problematic to get satellite reception. It's called a repeater. Yes, these are terrestrial repeaters, and they use a different waveform than what is used from the satellites. Satellites use something called single frequency time division multiplexing. On the ground, they use pretty much the whole communications industry has migrated to something called COFDM, coded orthogonal frequency division multiplexing. It is a format that's very different from the signal waveform from the satellite, that is very robust to primarily reflections off a building. Because that's the big problem that you have with any terrestrial repeater, whether it be 5G or Sirius repeater networks, is when the signals start bouncing off buildings or basically anything. You're getting multiple copies of the signal at your car, and that could be very problematic for certain waveforms. COFDM was designed about 30 years ago, and it handles it quite well. So each repeater on the ground, there's about 600 of them, and each one roughly sends out about 1,000 watts. Yeah.
So when you talk about the method that's used to handle dropouts, not in an urban area,
I'm going to talk about that. Yes, that's coming up. Yes.
How many of those repeaters in Manhattan? Because one of them was right next to our clubs and machines in Manhattan. So I was curious how many there were.
Yeah, in the New York City area, meaning the 5 boroughs, including basically a long strip of road along the New Jersey Turnpike, around Rutherford, and parts of Connecticut, there's about, I believe, 85 repeaters there. Within the island of Manhattan, I believe there's around 20 or so repeaters. Yeah, they're scattered throughout the city. Mm-hmm. And the combination of the satellite and the terrestrial repeaters provides for a very robust coverage. It's at 5 nines, which is not meaning 99.999% of the time you're going to get reception. This is far better than the cellular network. Okay. It has to be this way because what you may not realize in a cell phone, particularly, well, primarily when using data services, if you don't get reception from a piece of data that's sent to you, well, they use something called automatic repeat requests. They'll go back to the transmitter, say, please send it to me again. So you don't know that maybe the first attempt failed. We don't have that luxury. We can't talk back to a satellite 23,000 miles in the sky. Plus, we have 35 million people listening to the same thing. So you'd have a lot of requests. So you have to design this system to be extremely robust and redundant. And I'll go into how that is so. Okay, this is the terrestrial network, a map of where the repeaters are located. And again, it's a combination, there's about 600 of them in 70 major markets. And that covers about 60% of the population, okay? Now you'll notice where they're located, it's again, where the population is high density. California and the East Coast here. You'll notice there's not a single repeater in Wyoming because there's only 400,000 people there. And it's very flat other than the mountain range of the Rockies there, but no one lives there. So we don't need a repeater there, okay? It's very much dependent on the topography and the population that will dictate a repeater. And initially they rolled out with about 2,000 repeaters. They found out that was overkill, and now we're down to, I think the exact number is around 578 or so. Okay, so you're driving around and you're actually at any point in time pretty much always picking up the satellites from the West Coast and East Coast, okay? Unless you're in an area where they're being blocked, like big buildings. And at that location, you are picking up a terrestrial repeater, let's say in Midtown Manhattan, where the satellites, both of them are being blocked, so you actually pick this up. So there's always a continuous coverage. There are times where you'll actually pick up all three of them, okay? You're driving along the Jersey Turnpike, you have a clear shot of the sky, and the tall buildings are far enough away, and the repeaters are at the top of buildings, so they are not blocked. The satellites are not blocked. This is not blocked. You're actually getting all three. That's the time where you're getting the most robust reception. Now, if anyone familiar with radio frequencies and channels, and for those of you who are not, bear with me on this. Basically, this is the center of our band at 2.3 gigahertz approximately. And this was the 12.5 megahertz that CD radio purchased. And here's what XM, they were basically butted right next to each other, which was convenient when we merged because now you can have one tuner that can actually capture all 25 megahertz. But here is where this section in green here is what was the Sirius East Coast satellite. Here was the West Coast satellite. And these guys here were the this satellite here, this waveform, and this waveform came from the East Coast for XM. The next one over was for the West Coast, and then in this beige type color was the terrestrial repeater for Sirius, and here's a terrestrial repeater for XM. Now, the first thing you'll notice is that it looks like there's 6 different channels for XM and 3 for Sirius. And that was done because from the start, they designed this network to basically generate this signal based on the satellite signals. The Sirius signal did not do that initially. So what happens is it receives these outer satellite signals, and that is used to transmit. So A generates this A and B generates this B on the ground at a terrestrial site. Yes?
What's that actual center frequency? Is there an extra digit? I'm expecting it to be halfway between 2320 and 2325.
This is the exact center, 2.3325.
Oh,
That's 232. Is that a mistake? It should be 0.5.
okay, that's
Yeah,
what I was trying to
yeah.
figure out. Got it.
Yeah, sorry about that. Yeah. Yeah, it's exactly 12 and a half from here. Okay. And the reason they did this is because when you start transmitting this is a very high power signal, much stronger than your satellite signal. And what happens is these guys get knocked out, but they're redundant. So you can still recover this outer satellite here for A and B. That became a lot more difficult doing this approach, but we recently converted over to the same thing. I'm not going to go into that. But what we used to use is something called a VSAT, which stands for Very Small Aperture Terminal. It was a private network that we would rent time from to send data to terrestrial sites to be able to transmit this signal. We did not reconstitute this signal from one of our own satellites. We just recently moved away from that, and we do now reconstitute it from this satellite here. That was a little difficult because once you start transmitting this starts clobbering this. So how do you maintain reception on this guy when you're starting to transmit here? But there is some innovative signal processing involved in that. Okay. So a typical reception scenario is the following. If you're near a terrestrial repeater, a big city, you're primarily going to get just the repeaters from that are on the ground. And the reason is because they're so powerful compared to the satellite, the tuners cannot discriminate the vast difference in power levels. It's greater than 1,000,000 to 1. But when you go away from the repeaters, you actually start to pick up a combination, and I'm showing it in blue, where you're picking up not only the repeaters, but also the satellites. Well, this blue is the best reception you can possibly get, because that's called three-stream combining. You can actually receive the satellites and the terrestrial. When you continue to go even further away from a terrestrial repeater, and that's usually at least around 40 miles or so, then you're not picking them up at all, and that's what's shown in green, and then you're relying solely on the satellites, okay? All right. All right, so this was to one of the questions. So how do we make this so robust? Because I'm not ever able to talk back to the satellite to please send me something that I missed. And there's 35 million listeners, and they cannot all be asking this. So this is known as a broadcast network. It just sends out, and if you get it, you get it. But we want people to get this as reliable as possible. So there was a lot of effort involved in this. And what we do, and the way you do it, is you basically build redundancy into the waveform. So there's many forms of redundancy, but here I list are the 4 most popular ones. And I think the first 2 are fairly easy to understand. So let's first talk about spatial diversity. So I said there's 2 satellites, and they're both sending the same information. Well, if I'm driving around and let's say I'm blocked by one of the satellites, there's a possibility that the other satellite is not blocked. Well, as long as I get one of them, I'm going to play audio or receive my data services. So that's a simple thing to understand. You have 2 satellites pretty far spaced apart. One's on the East Coast, one's on the West Coast, and you hope that they're both not blocked. But obviously, that doesn't always work. So there will be times, and many times, where both of them are blocked. So we need to go to yet another form of diversity. Well, not related to blockage, but more so to interference, is we also use frequency diversity. So each one of these satellites can't send out their signal on the same channel, or else they'd be talking on top of each other. So they use separate bands. And now that's good because there is a cell service right next to each of our satellite signals. Well, if you're near a mobile unit that's talking on its phone, there is a possibility that that could clobber one of our signals. Well, okay, but you still have the other signal that won't be clogged because it's further enough away to not be affected by that service. That's called the WCS band that primarily is owned by AT&T. So the last 2 are the ones that really are the trick on how this is done. And that's time diversity and code diversity. So I'm going to have 2 slides on each one of them. So time diversity is exactly what it says. I have 2 satellites sending out the same signal, but I'm going to do something very clever. I'm not going to send them out at the same time. I'm going to send them out the same content at different times. And I'm going to separate them by a couple of seconds. And it turns out it's roughly around 4 seconds. So let's talk about that as one slide. So let me show you. Here's the Sat-1. Let's imagine this is the East Coast satellite. And let's say this is the West Coast satellite. And notice that the West Coast satellite, I'm going to have a block of data. I just label it as the letters of the alphabet. But block A from the East Coast is sent now. Block A is sent a bit further in time. So imagine the X direction as time. So you're delayed in time. So all the data is delayed by 1, 2, 3, 4, 5, 6 blocks. Okay. So it's exactly the same thing. from Sat1 and Sat2. Now, above it is, I made this very idealized, assume that you're getting perfect reception, and then for some reason your car drives around a building and both the satellites are blocked. Okay, and then you keep driving and then you come out of the blockage and you get your reception again. Okay, so obviously both satellites are going to be blocked and you're not going to get reception from either one of them. So that's this shaded out portion here. But the key is you're losing different portions of the same content. All right. So now at the receiver, what they do is they will delay, all the receivers delay the undelayed signal by the same amount that the delayed signal was sent out. So what we have here now is what you're receiving here is what was received, but I'm going to delay it by the same amount that the Sat2 was delayed by. So in the receiver, I see the blockage actually being dispersed in time now, okay? Because there's an internal buffer in all the radios that do this for me. So now at the receivers, there's something called maximum ratio combining, where I take the signal from the first satellite and the second satellite. Think of them as basically just adding them together. If I have the same content, I just add them up, divide by 2, and I got the original content. But if I have nothing here, I got a 0 here. So what you're seeing here is in the green is the summation of the two. And this is a very, very robust reception. I didn't have anything here, but I still had this guy here that wasn't blocked because he's now at a different time. So I can reconstitute the original data, even though I had an outage here in time, and I have no loss of reception. Okay, is that clear? So that's called time diversity. It's a very simplistic way of doing it. Turns out there are more clever ways of doing than what is shown here. Okay. Okay, so now this one's a little bit harder to understand. Does anybody know about what a parity bit is? Anybody? Okay. Okay. So the data is sent from the satellites, and what we do is we use something called forward error correction. So not only does the bits of, let's say, your music or your nav maps or stock prices get sent out, but we also send out some redundant information based on that information. So if I have 100 bits of information, I might want to send out yet the original 100 bits and then an additional 100 bits. Okay, so I'm not going to send out 100, I'm going to send out 200 bits. That's called forward error correction. Forward because I never go back to the source and ask for a retransmission. So if there's a problem, I'm going to try and resolve the problem locally based on the redundancy that I am using in my waveform. Okay. So what we do is we use something called a turbo encoder. I'm not going to go into the details of that, but just think of it as a device that takes some information that I'm showing in the beige here of data, and it could be anything. It could be stock prices, music, I don't care what it is. And I'm going to put it through this magical device that sends out the original data, and then additional not copies of it, but different versions of it. Think of it, okay? But any one of these can reconstitute the data. So I don't necessarily need to even receive this. I can get any one of these and I can go back to the original data. That's basically the concept of forward error correction, okay? Now, we generate so many parity bits that what we can do is, because remember, if I sent this over one satellite, it takes a lot of bandwidth to do this. So what we're going to do is over one satellite, and this is in addition to all the other diversities that we've been talking about. I'm going to send the original data, and let's say I send the first 2 batches of these parity bits, and I'm going to do that over the Sat1, which is the East Coast satellite. And I'll do the same thing over this West Coast I'll send the original data, and then the next two batches of parity bits. So now, and any one of these can reconstitute the data. So if this is going through a fade, I can reconstitute, and this is going through a fade. And then at the receiver, also, by the way, at the terrestrial can also send out a different copy of, let's say, parity 1 and parity 4. Okay, so each one of them is sending out the original data and different parity bits. This is called code diversity. All right, so you're basically receiving a signal that has some built-in forward error correction that will allow me to reconstitute the data. If the data gets wiped out or if the parity bits get wiped, it doesn't matter. I can get back to the original data. And any one of these three can do it. But the beauty of this is that because I have so many of them at the receiver, I can bring back to my original encoded sequence of the data and then all 4 copies of the parity bits. It turns out that that's a very robust way of trying to handle fades, okay? It's better than any one of these individually by far. But you don't always, not always guaranteed. It depends on whether you're receiving the signals. Okay, so what are the challenges that we face? Well, reliably to get this, it's very difficult. I have an entire satellite radio here, and it's amazing what this thing will do. This is basically a supercomputer, and pass this around. You can take a look. The actual satellite radio is this little metal chip. That's the entire satellite radio. You plug an antenna to it, and you plug it into a data bus on the car, and you're set to go. Okay, so what are the problems? Well, like one of the folks in the audience said, yeah, we got bridges, tunnels, and so forth. And how we handle it is those forms of diversity that we talked about. But I've shown you something what was known as just a very simplistic model of the signal being present and then gone. The reality is that it's a much nastier thing. It's actually coming and going hundreds of times per second, and it's not simplistic at all. Okay, so, and I'll show you exactly kind of what it really looks like. So this axis is time, okay? And this is, think of it as a signal level. So you got a good signal here, then it disappeared, went back a little better, got that, went way down, and it's basically random, okay? This is very challenging to receive. All right. So the network that we use in the terrestrial network is we have multiple repeaters. Now, the question you might ask is, well, how do these repeaters not clobber each other? And that is done by what's known as a single frequency network, where every repeater on the ground is transmitted on the same wave, same channel, which is different from the cellular network, which uses a multiple frequency, okay? The reason you can do this is because the waveform is designed to handle exactly this type of orientation. And there's something called a guard band. I'm not going to go into the details. If you want, I can explain it to you after the talk on how this is done. But it's a very fairly simple and straightforward way to design the waveform, and the receiver can handle all sorts of reflections, whether it be from a transmitter bouncing off a building or you receiving not only one transmitter but multiple transmitters, because they're all sending out the same thing. So that would look like a reception from a reflection from a building. But in reality, these 4 signals that arrive to the car, they can come from a building reflection, or they can think of it as other repeaters in your local market. It's transparent to the receiver. So what does this look like in reality? Again, this is the Jersey Turnpike. How many reflections am I seeing when I'm driving up towards the George Washington Bridge? Well, I can clearly see 1, 2, 3, 4, 5, and a little smaller one here, 5 or 6 or so. These are not really reflections. These are multiple repeaters that are being received from Manhattan. Okay. And this is a snapshot in time. This is time versus amplitude. And if I do it over the entire length of the drive, you can see, I believe the time starts here and goes down. You can see this spread out, and then it actually is varying. And there's a reflection that went out this way and disappeared, popped up again here, and then disappeared forever. But they also will change in the arrival time, because again, this is time, and this is in microseconds, by the way. Okay, the receiver has to handle all of this. All right, so inside that module that's being passed around, there is a lot of stuff going on. Okay, there is a tuner. There are multiple what's known as channel demodulators that take the waveform and try and basically turn it into the raw information bits, and multiple forward error correction decoders. Ultimately, there's source decoders, which is what is going to play your compressed music to, you know, the music that you enjoy listening to. This is all done primarily in software on high-speed processors. In the latest chip, we're going to have 13 demodulators and 3 high-speed 1 gigahertz processors per second running inside the receiver. This is an older receiver. This is, again, essentially the entire receiver here. This is the entire satellite radio receiver. This was the tuner, and this was a memory chip. And to give you a relative size, there's a quarter on top of it. Okay. The module that's being passed around, we do all of this. They're about $10 or so. How do we do this? Now, this might be a little bit technical for some of the folks here, but this talk was initially for the students at TCNJ. There's a very high-level analysis done in a language called MATLAB. It's just a mathematical exploration language. And we use that to refine how we're going to basically build a receiver in terms of loop gains and time constants and filters and so forth. What did it take to do this? Well, it took about 12 engineers who are specialized in digital communications technology, and it was all written in a very high-level language called VHDL. For those of you who don't know that, what this is, it is yet another computer language, but it's a very special language in that when you write in this computer language, there's software called compilers that will take the language and design hardware for you. So it's kind of amazing, okay? It took about 5 years of the 12 engineers working on this, and it's about 2 million lines of code to do this. I don't know the gate count, but it's billions of transistors that are in that chip. All of it was designed here in Lawrenceville, New Jersey, and the chip was actually manufactured in Catania, Italy. And the module was assembled in Malaysia and then shipped back to Michigan to go into the cars in the US. We only are in the US. We don't put our modules in European market cars because our satellites don't exist over Europe. They only exist over the US. We do have customers in Canada, and we do have some customers in Mexico. When we design this, we basically, before we actually spend $2 million on what's known as a mask to generate these computer chips, which are known as ASICs, which stands for Application Specific Integrated Circuit, we have to prototype out the design and make sure that everything is working as it should be. And what we do is we use something called an FPGA, which stands for Field Programmable Gate Array Logic. It is a device that you can purchase that can be reconfigured to do your hardware, okay? And we load the design onto this platform here. We have a portable laptop and software to run to basically put this in a truck, drive around, and make sure that the reception is as good as we want it to be. do have some time left to show a demo of that piece of software. So let me just bring this. Oh, no, I can't do that. It does, I'm sorry. Okay. All right, so that's unfortunately, I was planning to do a demo of some of the software that's used to evaluate this, but I can't run that. So that's pretty much the end of the talk. I'm open to any questions. Yes.
I have a question on the, when you want to skip a song, you know, you think you get like 8 and so, but more than half the time it doesn't work.
Well, that can be blamed on somebody else, not me. That kind of stuff is done by the application software, which I'm not involved in. Sometimes you're limited by the music industry on skipping songs. It's just a policy that we have to abide by. So it probably is not the technology, it's probably a license agreement with the music industry.
Doesn't work at all.
Yeah, I don't know.
Okay, 2 questions, but one has 3 subparts. Why the orbit shift from synchronous to geostationary?
Okay, let me answer them as you throw. Okay, so initially when Sirius was launched and XM was launched, XM always used geostationary satellite. That means they're always in the sky at the same spot. Sirius decided to do something different. They decided to launch satellites where they're constantly moving. And they move, if you were to look at them over a projection on the Earth in this big figure 8 pattern. And we had 3 satellites that were always moving. They were basically chasing each other, always in this figure 8 pattern. And the reason that was done is because that's actually a superior, what they call satellite constellation in terms of signal reception, because it's higher in the sky as opposed to being at a more shallow slant angle. The problem with that is there's no good sparing strategy for that. And they recognize that if one of the satellites goes out, we're in big trouble because you really needed 3 satellites. 2 were always over the US and 1 was in South America recharging its batteries. So other than, and you can't have 1 spare satellite just parked there because the physics of it and the dynamics of the fuel and whatnot, you can't get a satellite to go chase and catch up to a satellite. It has to be launched in a trajectory. So there was no sparing unless you were to have for all 3 satellites, an extra satellite basically tagging along with it just in case it failed. That would be 3 times the cost. So they decided many years ago to abandon that constellation and move to a geostationary.
The other questions are about the satellites. Who makes them? Who manages them? And are they a custom design for Sirius?
Yes, they are definitely a custom design. Almost all satellites are custom design. They were built by Loral Space Systems out in California. An interesting fact, they cost about $100 million to build. Launch is about $100 million, and we always ensure the launch and the satellite to be functioning properly. That's another $100 million. So every satellite we put up costs us $300 million.
And L'Oreal maintains.
No, the station keeping is done by Intelsat. Yeah, different company. Yeah.
So you mentioned earlier that in Europe or any other country outside of the United States and Canada, these chips or the cars would not be able to support. But how about if you subscribe to SiriusXM and you're in Europe, could you still do the streaming though?
Yes.
Over the internet?
Yeah, yeah, yeah.
So there's no.
Yeah, the streaming, primarily people do it on their phones. So yes, yeah, it would work, certainly.
One of the slides said, Star's satellite signal. Why would that be a problem? Receiver the receiver.
Because remember on the early slide, the satellite signal is coming down to the Earth. It's about 1 femtowatt. The terrestrial repeater puts out 1,000 watts. So that's a 10 to the 18th magnitude difference. So what happens is it can, if you're far enough away, you can certainly receive both. But when you get very close to a repeater, the signal amplitude coming from this repeater is so much bigger that there's just not enough dynamic range in the tuners to reproduce the satellite signal with any kind of fidelity.
Still detect here, so having the computer overwhelm the satellite.
It's not a problem. It's not a problem.
The other question I had first, when you shifted the line together,
Yeah.
you have to put the configuration of the receiver location.
Yes. So what happens is the receivers are constantly putting the signal through what's called an elastic buffer. So yes, the signal is, that was, okay, here's an interesting story. In the early days, that's a good question. I'm surprised that you asked that. The signal arrival time is always varying because the satellites are moving a little bit and the car is moving too. So the electronics is always handling that. And it's always measuring the time difference around between the two signals and knowing how much to delay one versus the other. Okay, an interesting story is in the early days when they had the polar orbits, the satellite at its highest speed was moving at 9,000 miles an hour. That created a huge Doppler, okay? And what happened was when the cars were driving around and going through a fade and it was blocked by a tree or something like that, it would come back and it would actually arrive at a different point in time. Now, remember, we're trying to combine these two signals. And now you had to, and this tripped up a lot of people, you have to recognize that all your buffer data is now invalid because you're adding to the buffer a portion of a time shift. But you got to recognize that time shift. And it was very hard to figure that out. And what was happening is that you were combining the two data that were not to be combined. They were out of alignment. That was called a miscombine. That almost sunk the company. So it's a little bit more complicated than that. Yeah. What the trick is, you have to throw out all the old data, basically. But that's how this office in Lawrenceville was started. There were three companies: a Korean company, satellite company, a company in Maryland, and Bell Laboratories in Whippany, New Jersey. All failed to build this receiver properly. The early receivers were terrible because of that problem. That problem pretty much was never existed in the XM side because they were stationary. So the arrival time were pretty constant. They didn't vary much. But when you had the motion of the satellites, that was a big problem.
So how did they compensate that?
By designing the radios properly. So that's why we were hired. And basically the founder of the lab in Lawrenceville, he was very lucky in that he had a bunch of communications engineers who were designing this kind of stuff. I was one of them for many, many years. And we kind of like knew how to do this, where the other companies, they didn't put their 18 on it, basically. Yeah.
So obviously one of the applications you have is carbon and also the streaming service. At one point, was there a physical radio that you could carry around?
Yes. Yeah, I think they're still available.
Still?
Yes, there was a handheld. I don't think you can buy it anymore. I'm pretty certain you can't. Yes, there was and it actually recorded music for you too. But that's no longer available. They don't make that, but there are still portables. They don't make too many of them. Where let's say you had an older car that didn't have SiriusXM. Every car is built with SiriusXM now. But if you didn't, you could actually have a little module that could sit on your dash.
And an unrelated question, I'm in a new car that has SiriusXM. Can you tell us a little bit about Tunestar?
I'm not familiar with any of that stuff. Yeah.
I tripped over it completely by accident. So you have like 15 presets for your stations.
Yeah.
Apparently the radio is actually listening to all of them.
Yeah.
So that if you do a track change,
Yeah, you go right to the beginning of the song.
You go to the beginning of the
Yeah,
song.
you want to know how that works, basically?
Do they encode something that winds up saying this in the song?
Yes. Yeah, yeah, that's done by the firmware team. I mean, I can tell you what I know of it. So when we receive the signal, we are actually decoding every single audio channel. They're all available. Okay, there's what, 150 or so music channels. Every single one of them is decoded simultaneously. Now, in each of the radios, there is a memory chip that has limited space. So they basically say, okay, well, we're gonna let the radio record, roughly works out to be about an hour or so of your favorite channels. So you can select upwards of, I believe, 20 or so favorite. If you only had one favorite, then you can have a lot more recording for that one channel. Obviously, it's split among how many favorites you have. But in the waveform, at the application layer, there was a marker that says when the song starts and when the song ends. It's approximate. It's not exactly perfect. It's a little hard, and it's a little nebulous because there's crossfades of songs coming in and out of each other. But there's roughly a beginning and an end, and that is noted, and that tells you where the beginning of the song is. So they're always recording your favorites in this buffer, and then when you go select your channel, you get to hear the very beginning of the current song being played. So it actually jumps back in time to play.
How many transponders are on the paired set? It's just one, or you have redundancy?
It's just one.
It's just one. Okay.
Yep, just one. Yep.
So I want to miss something somehow. You said that there were 5 satellites.
One's a spare.
One's a spare.
Yeah, one's a spare that can handle any one of the 4 that go. So the spare sits in the middle of the US.
Really?
Yeah, and because it doesn't know whether it has to go to the East Coast or the West Coast. So there are 2 satellites per band, Sirius and XM band, each use 2 satellites. So that's 4 right there. And then 1 satellite, and they're all designed to be interoperable. Okay, in the early days, they were not, but now they're all common. It's one common design that can handle both bands. And it sits in the middle of the US. And right now, that was a $300 million investment that's just sitting there doing nothing. So we hope we don't have to call it into service. So there's a big effort. I'll give you a little insight. Well, that's silly to have this thing sitting there doing nothing. So in the future, that will be used for background stuff that you won't know if it ever is taken away from you. Like downloading files, nav maps and stuff like that. We don't do that yet, but it's coming.
So over the operational lifetime of the satellites, I think since at least when I was there, I'm guessing that you've deorbited at least once, right?
They've actually deorbited, well, that's another interesting. No, they've actually deorbited about 5 or 6
Okay,
now.
so they just burn up over.
No. So what they do, most people don't notice, is that everyone does this. There's a graveyard way up in the sky. It's at around 35,000 miles above the Earth. They actually take the satellite and make the rockets push it up to this higher orbit. And then at that orbit, they estimate it'll take anywhere from 10,000 to 100,000 years before they fall into the Earth. And by then, it'll be someone else's problem.
So by that
That's
time,
literally what they do.
yeah, we can't.
That's
get those-
literally what they do.
We can't get those parts over in the room over there with the electronics.
No, off the sat, no. And if it did come down, you ain't gonna get anything out of it. Yeah,
So they don't say they're at station. Are they doing that in the US or somewhere else?
no, it's here. Yeah, they have to because they can't receive the signal anywhere else. So it's done here. Yeah.
That's like,
Yeah.
Holly, Pennsylvania, or the control still there?
Okay, so they have, because they need to triangulate on where the satellites are. There are multiple locations. I don't know exactly where they are. Just another point of interest, our uplink, we take care of our own satellites. They do the station keeping. That's called flying the satellite. We used to do that, and then we realized that's not really our business, so let's contract it out. And some executive was able to lay off a whole lot of people. But anyway, but we still take care of our own satellites in terms of the uplink of the equipment. So that's done in Vernon, New Jersey, or it could be done in Ellenwood, Georgia. And actually Washington DC too. So there's 3 uplink facilities and there's multiple studios. There's one in Miami, New York, Washington, LA, Tennessee. They're scattered throughout the US. All the data gets aggregated and sent to these uplink facilities and then sent up to the satellite.
Is there some kind of private network that gets them to the uplinks? Or do you-
We have like T3 lines that we own. Yeah. So that's a dedicated lines.
Something I've always wondered, if you only have a one-way communication to the receivers, how do you do provisioning of new radios? Like somebody gets a car and they want to sign up for the service. How does that work if you can only, the radio can't request, you know?
Okay, so the modern radios now, you can do that over the 5G network, because all of our radios now have a cell phone modem that go along with it. But prior to that, basically you were told to turn your radio on, and when you called up, there was an operator, you usually were in Singapore or someplace like that, they would type into their computer and it would send you an activation signal. It would be embedded inside the waveform.
So you have like a window of time.
Yeah.
Where it would be. Sent.
Yeah, they would send that out multiple times. They would activate the radio. And then they have to send a keep alive signal. So if you stop playing, they don't send you your keep alive. You need to receive it once in a month, 1 month period. Your radio will stay on. So if you cancel today, your radio might stay on for another month.
Eventually it wouldn't get that.
Right, eventually it's not gonna see it. They didn't do that. In the early days, they sent an activation set, and then they had to send a deactivation signal. Now, what's the problem with that?
You don't
Well,
get
guess
the-
what? I can hide my radio in the closet and it never gets deactivated. But then I can't use it. But what people didn't, well, I think they realized the deactivation signals would be sent out, but if you're gonna keep deactivating so many radios, you're gonna use up all your bandwidth. So they would deactivate frequently, and as time goes, they do less and less and less. Eventually, they stop deactivating. So if you hid your radio in the closet for a year or two, they'd stop sending, and then you'd have a radio for life. But they kind of got around that, so that doesn't work. Anything else? I think my time's up.
Oh, you started that, it's the airplane one?
I don't know. This was satellite radio.
And Shell's still there.
Yeah.
When you're driving down the road, Route 1 or whatever, and you get momentary dropouts. 1, 2, 3, 4, and then it comes back on. It's just kind of freaky. But so is that?
Yeah,
like
okay,
change
so
in
you,
satellite or
so,
something?
no.
I'm not driving up
No.
trees or anything, but
No, so when you do lose it, yeah, I'll find it. When you do lose the signal,
you know, it's like momentary.
yes, yeah, you're probably not next to a repeater. All right, so that's the first thing. Okay, you almost never lose the signal with a repeater. So then now you're basically relying on the satellites only. And if you have a blockage that exceeds that delay between the two, then you can't recover the signal. So usually there was some kind of distortion that was prolonged enough to basically you to hear that.
Yeah, it's just once in a while, but you know,
Yeah.
it's like, you know. it's like-
If you were to go around and
2
see what the
seconds.
signal is doing from the side, it's amazing that even
Oh, yeah,
works.
yeah.
It really.
Thank
You
you.
give up to ham radio clubs,
I can if you want, sure.
when you have a card, okay, I go to one in Georgia.
Which club do you belong? to?
Linemark,
Where's that at?
they're in Long Island, it's Long Island Amateur Radio.
Oh.
Long Island Mobile Amateur Radio Club. One of the directors.
Sure.
There you go. I was out in Arizona
You got almost
driving a
400
renting car maybe 2 years ago. And when I was driving mountains on either side of me.
Yeah.
I'd lose it for like 5-10 minutes.
Yeah, there's no repeaters out there,
Yeah.
and if you have a mountain blocking both sides,
Yeah,
you're kind of screwed.
yeah,
But the thing is, there's not a whole lot of people there, so
yeah, it didn't really matter that much.
where there is
But-
people, the
yeah.
reception is pretty
Yeah,
good.
but the other thing was, at least the XM satellite radio worked. There was nothing on it.
Oh, there you go.
Yeah.
No, we can cover the entire United States, 500 miles out on the ocean for cruise liners.
Oh,
Most of Canada, except the very, very northern, where no one lives.